Yes.
Okay, great. We are good. All right. Sorry about that. Okay, let's um let's do that one more time.
Should we start? Yeah.
Yeah, all right, Jordy, start one more time. Sorry about that.
Well, yeah. Hello, I'm Jordi Bailina. I'm the technical lead at Polygon Hermes. We developed the zkEVM. And yeah, mainly from the code side. I'm mainly responsible for the prototyping, the JavaScript part. I created the PIL and the PIL language and the ROM and very much a lot of the design part.
Perfect.
Maybe
Okay.
Francesc or yeah.
Okay.
Well, Francesc, go on.
My name is, hi everyone. My name is Francesc Romero. I'm in the Polygon Hermes team. I work in the prover component in the C++ version. So I'm the counterpart of Jordi in the C++ world, and I mostly specialize on the executor. We'll see what it is from us.
Cool.
Okay,
Carlos,
thanks,
maybe.
Francesc. My name is Carlos Matallana. I'm the team lead in the protocol and integration team for the zkEVM. And basically what we are coding is the smart contracts and what we call the ROM, which is the interpreter of the zkEVM in the language that Jordi invented, zkEVM. Now, Arnau.
Hi, I'm Arnau Ben Nassar, and I'm working on the node or the client, what could be kind of the guest of the zkEVM project.
Cool. And I'm Kelvin. I don't work at, at Polygon. I work at Optimism, but I always like to hear about how other people's code works, especially zk code, because I look at some of the repos and I see all these different folders, and I have absolutely no clue what any of them means. So cool, yeah. So this is, I guess, the goal here is to try to get a better understanding of what the architecture is, and then explicitly to also map that back to actual lines of code that do the thing that the architecture wants to do. So do we? Can we start with like what is the high level architecture? We know what, I guess, let's assume that we know what a zkEVM is trying to achieve. But let's get into how Polygon, the zkEVM, achieves that.
If you want, I can do a brief introduction, 2 minutes explaining that. I don't know if I can share the screen. Is it possible?
Yeah. Feel free to share the screen for sure.
Yeah, well, let me share the screen for a moment. There it is. Okay. So, well, yeah, well, let's see. So the main idea first to understand very much what the user sees is the user. There is a sequencer. Okay, so a sequencer is a centralized. In this case, it's a centralized sequencer. So the user can send transactions to the sequencer. So you can have an API and have a sequencer here. You get a state. So the sequencer just takes these transactions and keep it. And if you trust the sequencer, you are done. You're fine, but it's centralized. So this is not nothing special here. So the sequencer, once in a while, what it does is just takes these transactions and send them on chain. Okay, they pack these transactions and they send a transaction with with batches. With many batches. Each batch may have many transactions, and all of them go off chain. Okay, this already is an implicit state. We don't know which state is, but you deterministically can process all the transactions that you send blockchain.
Interesting.
Okay, so this is the part. So and then there is this implicit state. So transactions are final. So you cannot. Everybody can calculate this state, but this state is not now by the blockchain. So at this point, you cannot withdraw the funds. So it is later on that there is a prover that actually takes these transactions and computes a proof, which is a real state, and put this state on chain. And this at this point where you can remove these. So withdraw the funds on here. So these 3 steps. Just send to the sequencer, centralized sequencer. The sequencer sent to blockchain. Transactions are executed, but are ready final, but you cannot withdraw because the state is not calculated, and then the prover which actually puts the state, the real estate. Okay, so yeah, so here it's a little bit the big architecture. So in the big architecture, well, here, let me go here. So there is in one side is the smart contracts. So we have all the smart contracts. This is in the repo of the contract. See here, mainly we have 2 smart contracts. Actually, it's more, but mainly is for the what's related to the bridge and what's related to the rollup itself. Okay, we call this contract proof efficiency because it's the protocol that's using, but it's the rollup smart contract, the main rollup smart contract. Okay, then we have the node. That the node is very much like, as Arnau was explaining, but it's very much like a client. Okay, so the node has these main 4 pieces. Okay, so in one side we have the synchronizer. The synchronizer mainly is a model that's just reading constantly the blockchain, and it's actualizing the database, is actualizing the state. So it has synchronized the database, so it syncs the blockchain with the database itself. We have the executor. The executor mainly does this, so it's the one where you can receive the receive the transactions and mainly have all the transaction pool, select the transactions, and sequence these transactions. So the executor is the sequence. Sorry, executor is not executor. It's sequencer. Huh? This is let me just go back here. Right. Okay, and then we have the aggregator. Then we have the aggregator. That mainly what it does is this program. It's a separate program that actually is reading also the blockchain, but it's computing the proofs. Okay, so the aggregator actually is connecting with the prover that's actually is doing the proof. And here we have also the RPC, because this node works very much like an Ethereum client, and actually it's 100% compatible like an Ethereum client. The RPC. So normal RPC interface, so you can query the state, query the transaction, the transactions, the blocks. So it should be absolutely. The idea is at the end is that the user that's deploying on top of the zkEVM it should be exactly the same that working with Ethereum. They should not notice any difference at all. They just connect to a different endpoint, and they should see exactly the same. So this is the compatibilities with this RPC part. Okay. Then we have the bridge, which is mainly handling it. So the end is handling all the interface with the smart contracts and the UI of the bridge, which is these 2 repositories, a backend, a front-end, normal application on that. And the main part is the prover. Okay, so this is at the end the aggregator. At the end is asking for proofs, and then it's a prover, which is the big part. At the end it's just computing this proof. So actually, what it does is very simple. We just take the prover is just take an auto-state route. You take a set of transactions and computes a new state route. This is the high level what's doing the prover. Okay, and then generates a proof. This generates a proof that actually this is correct. You don't need to process. You don't need to process all these transactions. It promises you that this is right, and it proves you that this new state is the correct one. Okay, so what's in the prover? Okay, so what are the pieces in the prover? So how the prover is built?
For 1 second, can I go back to the
sure.
Just where were we? The basic architecture that we were just looking at. There we go. Perfect. It's funny. I just wanted to say it's funny that this is almost exactly what the components that. I mean, besides the proof mechanism, this is what optimism looks like, right? I think this is like a high level. This is what
it's
roll-ups
exactly
look
the
like.
Same. It's a roll-up. It's
exactly
the only difference of optimism and this is that we are generating this zk proof. This proof that you don't need to wait 2 weeks. You need to wait 2 weeks for the challenge and this fraud proof. And this is it's a single proof that the prover just puts here, and then this proof the blocks. This proof that this state is valid. But the idea is exactly the same that any other rollup. It's a rollup. I mean.
Yeah. No, I just thought it's for people watching this stream, I think it's funny that we're at a high level. These things look. Very, I look at all these components and I recognize all these components.
Yeah, because it's like we learn from the optimism, from the optimistic rollups. It's in the community, so we're watching what the optimistic rollups, and we are just. I think that Optimism and Arbitrum both they set up a quite good ideas and good standards of what a rollup should be, and the value they added to the space, I think, is important. Okay, so that's the it's not a surprise.
No, it's not a surprise. It's not a surprise, and I think that it's a lot of this is just for the sake of the people watching this online. It's just like I think I want people to know that these things are roll-ups, and there's a reason why this all looks so familiar. But let's get into the meat of the differences. Let's get into the proof.
The difference is this.
Yeah, let's see.
Exactly. This is where all the magic happens. And actually, this is at least in lines of code, or at least in hours, let's say engineer hours. This is probably like 5-6 times bigger than the other part.
I'm sure.
So this is the important part. Okay. So how we build that? Okay. So this is how the prover looks like. Okay. So here the prover mainly has 2 parts. Okay. Mainly has at the end has a circuit, which is a processor. We just created a kind of a processor, a very simple processor. Okay,
this is a custom processor. It's
a custom processor, and it's a state machine. And this processor is validated with it's arithmetic. We have an arithmetization, okay, which is in the pill. Okay, so if you go to the pill, and this is in the prover.js, you see the pill. Here is all the arithmetization of this processor and all the components of this processor. Okay, and this processor, well, it's a processor. We can go a little bit in detail how this processor works. Okay, but this is the processor, and on top of this processor is the what we call it the ROM, which actually is the program that's executed on top of this processor. Okay, so that's the thing.
Yeah,
okay, so and here is the ROM. Is you can find the zkEVM in the code in the zkEVM ROM. Here you can find it's an assembly program that actually it's Ethereum. It just read transactions, it processes transactions, and it computes.
It's assembly.
It computes a new state the same
for
way
your processor.
It's an assembler. It's an assembly for our processor.
Got it. Okay. Sure.
So we can go to if you want to review the code, maybe we can go to the code of this ROM and to look a little bit to start seeing how it looks like. Okay.
Sure. So why don't you open it up?
I don't know if you want to go, but I can go. But this
no. You can go for it. Go for it.
Yeah. Sorry.
This is. I'm gonna say that I'll talk about this later, but this is very interesting to me. This is.
So here you go to the main, and let's see where this with everything starts. It starts in main, okay, and this is where everything starts. Okay, so this is well, these are comments, but this is the first line. Okay, so I'm just getting the global hash, so it's like. But this is the assembly, okay? And well, here is a special assembly. You need to understand this assembly. You need to understand how this assembly works. If you want, I can try to explain you briefly a little bit how it works. But this is a program that's just running here, okay? Just to go to some of the pieces, for example, you can go to the opcodes. Okay, so here is, for example, how you go to this is where the addition opcode, the sub opcode, the division opcode. You see here the mod opcode. You see here you have all the opcodes. So for example, they are interpreted here. But you can go. Well, here you have all the opcodes. All the opcodes are already implemented. Storage, create. Here is a self-destruct. Revert. So here is statical. Is the create to. So here you have all the opcodes in here. But here, for example, you can go, for example, to in the transaction RRP. Here is, for example, the parsing of the. Well, this is RRP, but this is transaction RRP. What is this one? Okay, so here you can see here all the parsing of the parsing of the RLP transaction. Okay, here's the non-thread. Here is the I'm reading the gas price. Here I'm reading here is the value. You see here is all the parsing of the RLP here. Okay.
Sure.
There is a part here, for example, there is AC recovers in this directory. For example, here we have all the AC recover. AC recover is done in a mixed way. So it's like we have in the it's a program that's doing the AC recover, but for the elliptic curve operations, the low-level elliptic curve operations, these are done by hardware. So they are done we have a specific module in the processor that's prepared for doing. So you don't need to deal with all the math. So it already, you can, in a single instruction, you can have a point addition or a point doubling or point doubling of the elliptic curve. Actually, are those two instructions, but yeah, that's the detail. Okay, but this is, so you don't need to spend clocks in doing that. We have like a kind of a coprocessor that's doing arithmetic operations. In this coprocessor, we are doing 256 bits additions, 256 bits multiplications, and so on. Okay, but at the end, all this in the assembly level, this is just converted to a single instruction in assembly. Then we can go low and go to the how the processor. So how the processor works. You know, this would be the software, and then the processor is the hardware. Actually, it's not hardware because it's
virtual.
It's arithmetic. Yeah, it's really a processor. It's a state machine that is processing and is doing these things. Okay, so this is the ROM, and you can follow that here if you want details. Carlos can explain a little bit more here on this side, but this is very much where you can see all the Ethereum, and then we can go maybe to the processor. I can just
I'll just so I want to sit on that for a second because that's
go. Yeah, I'm talking. It just got
no. It's okay. It's very interesting. You know, it's very. It reminds me of the AVM, if you remember Arbitrum's architecture. Very similar concept, right? They wanted to. They wanted a provable VM or an easy to prove VM, so they built this thing called the AVM, and then they built their own language on top of the AVM called Mini, and their own compiler for Mini, and then they built the EVM in Mini on top of the AVM. So this mapping is very familiar to me of having like a lower level virtual machine that's easy to prove, and then building in software, right? It's hard because it's not a real process. I mean, it is a real processor. It's a virtual processor. Very interesting. So I would say maybe the question then is why build your own processor? So let's say that for example you could take geth and you could compile geth down to your zk processor. I guess the question is maybe at a deeper level, why build a custom processor rather than proving an existing machine architecture?
This is mainly at this point is a problem. It's a matter of efficiency. Okay, so if you see it's efficiency for processors. Processors in the zk they work. So in the zk for having an efficient processor, you need to do tricks, and you need to do things that are a little bit special. For example, a processor in a zkEVM is not computing anything, or most of the things are not computed. They are validated, for example. And the way they work is that, we call what we have the free value. So that you have an instruction where you can put value that you want. So the executor, the one that the one that's running that's building this trace, the executor, they can put any value at that point, and later on you are validating that. For example, when you want to do a division, so you don't compute the division. The division would be very hard to do a division in zk. Okay, so what you do is you put the result. So you have an instruction that allows you to put the value that you want, and then you have another instruction that you can check that A times B equals C. So the idea is that you set B, and then you check that A times B is equal C, and this is doing a division of C divided by A. Okay, so this is equivalent.
Sure.
But you are not doing that in a computational. So you are not computing it. So you are checking that. So these things is one of the reasons why it's better to have a specific machine. But then there is there is another thing is an efficiency. For example, the EVM is 256 bits arithmetic. So the standard processor is not 256 bits arithmetic. So in order, for example, to do a single addition, it would be a lot of instructions. It would be very, very slow on itself. Okay, and the processor is not only the processor itself. You need to build the processor, you need to build the memory, you need to build the storage, you need to build some specific functions. Where I was mentioned before of this elliptic curve for the CDSA. So here what we did was instead of using a standard hardware, we created our own tailor-made hardware. So the idea is that we designed a hardware that's optimal to be run with this program. So it's a hardware that's designed mainly for this program, which is the Ethereum, the zkEVM. Definitively, using, for example, there is a project that's, I think it's called RIS0, and there is that's trying to emulate a RIS5 in top of that. This is definitively possible. You could get Geth and try to compile on there, but it would be very, very, very inefficient currently. I don't know, maybe in 20 years, the technology has advanced that much that maybe it makes sense to do that, but at this point, it would not be practical on that. So it would be very expensive altogether. And most of the pieces, you will have to implement it anyway, because you need to implement, for example, you need to deal with the storage, you need to deal with getchaks, you need to deal with this arithmetic, with this big number of operations. So at the end, the difference would not be very different. And in doing it this way is much, much, much more efficient. And that's why we decided. Also, when we started that, there was nothing of this available. So
sure, of course.
It's pretty much what. So here is where we are.
Okay, cool, great. So that makes total sense.
Here is for the processor. So just to give a big overview of what's in the processor. Here is the processor itself. The processor has a RAM, so you can have RAMs. This RAM is so you can do reads and writes, normal reads and writes like a normal RAM. With this RAM, for example, we divided this RAM in pages, and this allows us, for example, to do calls. So when one smart contract is calling another smart contract, you have like this concept of context. So you open a new context and you have different contexts, so you can have different memory contexts. Okay, so this RAM is structured in pages, and so we share this RAM for the EVM itself and for the system RAM. So sometimes for doing things you need to store things in memory. So we have this kind of organized RAM here. Okay, we have the ROM, which is the program that's actually executed, and that's this assembly. But we have a storage. Okay, storage is actually where you save the state. Okay, here is all the balances, the nonce, and all the storage the smart contracts themselves, and the values of the storage of a smart contract, the balances of a token of ERC20. So everything is here. So this storage is not the same that Ethereum. So it's not a Patricia tree like. So here is a very this is a sparse Merkle tree, and it's a very optimal storage that works very well with with the zero knowledge technology that we are using. We are using here very much the Goldilocks. So it's the Goldilocks prime. So it's a single. Maybe one of the things is a single storage. So in Ethereum, you have a single. It's a single tree, but then each smart contract has their own tree. Here it's a single tree for. It's a single tree for everything. At the end, it's a key value. Okay, and where the key is the hash, okay, and the value is whatever you want, and here we have a system just to access to this storage. And it's quite simple on that, okay. And we have a specific processor for binary operations. Here is the AND, source, XORs, equals, less than, signed less than in 256 bits. And this is a binary state machine that's doing these operations. You can understand this as a coprocessor. So we have an instruction in the main state machine that's equal, for example, or is doing an XOR, but then in the main state machine, it's just a very simple, it's just a clock, one clock, and then but then this processor is executed or is validated actually in another state machine. We call it a binary state machine. And we have another that's arithmetic. That's the one that I mentioned before. That's mainly for doing 256 bits multiplications, and also all these elliptic curve operations for the ECDS. And then there is a full topic with the getcheck, the getcheck and the hashing, all the hashes. They are also doing by hardware. So we are computed to have a specific state machines, specific hardware that actually deal with the getcheck, the paddings, and all that. These are the big pictures of the hardware. Okay, and then is the software that just running these instructions and executing this.
Okay, interesting. So you have, the storage is not a Merkle-Patricia trie. It's a sparse Merkle tree. You're doing that because it's more efficient. That makes sense. Let's see. Okay, you have all these clocks here. Is this? Can you explain what a clock is in this context?
Let's see where you are.
And
maybe you can share the screen too.
Well, I just saw on your presentation there you say
okay.
32 clocks per operation.
Oh yeah, this is like kind of an average, but the idea is that these clocks are instructions so are clocks of the main processor. So each clock is an instruction. So you're executing an instruction.
I see.
So in average, so what we are saying is that in average, and this is just a very it's an average. Okay, so but it's each opcode, each Ethereum opcode. Takes about each Ethereum opcode takes about something like 30-40, which is an average at the end is 16 clocks per gas unit. Okay, so this is a good average. This is not really real true because there are, for example, the storage instructions. The gas in Ethereum is very expensive. It can cost you 20,000 gas. Okay, and the real clocks and the clocks that you are consuming in the main processor is much lower than that. So this is one of the surprises that we get when we were putting this in the testnet, and is that actually the system. So in average, it works quite well. Because these high consuming instructions, they don't consume as much main clock processors, but they consume other resources. But you are not doing many of those. So in average, everything matches, and that's why we are saying now that in each batch right now we can put around 4 million gas in each clock.
Okay. Yeah, that makes sense. 4 million gas. Okay, that's not.
It's not. It's good enough. Actually, for example, here we deployed full Uniswap. Uniswap V3 was deployed on that, and everything without recompiling anything. Everything fits in there. and it works well. And Uniswap is, I would say, it's a good example of a complex system running.
Definitely. Okay, cool. All right, so I want to look at some code. I'm going to pull up some code here. I'm also going to. So here's where things get complicated, because if I share my screen, then we won't see it. Let's see. How do I want to do this? Maybe you could share your screen. We could take a look at the code and we can walk through it.
Just send me the link if you want.
All right, I'll send you the link. I'm still still figuring out the strategy here.
Send the link maybe here in the chat, and I will try to go.
All right, so getting down to business. What's more interesting to you? Which part of the code base do you think is the coolest to start with?
I don't know. Depending what you want to. If you want, one thing that we can do is we can take a transaction and maybe go to all the process. Okay, getting to all. We can go to the process.
Let's do that. I think that's a great idea.
On that. So, for example, when here maybe now you can share where all these RPC in the node is.
Sure.
You send the transaction there. Okay.
Sure. So let me actually share my screen. I think that it will be more smooth if I can go through it.
All right, so we'll follow it through that process that you described, going from a user to the RPC to the node to being sequenced and whatnot. Okay.
Okay, so this is the zkEVM node repo, and we are gonna do this journey. So starting from the RPC, going to the pool, then the sequencer will take transactions from the pool. It will use the state that actually uses the executor to decide which transaction to get into the sequence, and at the end, the sequencer will send this batch to Ethereum. It's what Jordi was explaining as the implicit state, and later on, the aggregator will take these transactions and build a proof. So we can start with the JSON RPC. Here is the JSON RPC implementation. If I'm not wrong, this specific endpoint would be here.
Got it. So this is a custom JSON RPC that matches the Ethereum JSON RPC.
Exactly.
Okay.
So essentially here, like you have the call, you have the chain ID, estimate gas, like all these methods that you would expect from the JSON RPC official Ethereum interface. And well,
you even have get compilers. That's
yeah. I mean, this returns something that is obviously bullshit, but but at least we have that. So I think that this should be send raw transaction, something like that. Okay, so then here we would add the transaction to the pool. And transaction to the pool. Well, this will end up adding the transaction to the pool. I mean, this is the RPC interface.
Yep.
To be honest, this is not the part of the code that I'm most familiar with. And here we will, I mean, the pool is just a database, so we store the transaction on a database, and then we jump into the sequencer. So the sequencer has, if we go directly to the meat, it has the batch builder, which is the first step that essentially, well, it waits to be synchronized with Ethereum. Then it checks if, so essentially this code has a bunch of logic to decide if we should try to add another transaction in the sequence, in the batch that we are working on, or we should close it. The decision is based on the amount of time since we have sent the last thing to Ethereum, if there are new deposits waiting that requires to update some metadata of the batch and a bunch of things.
Sure.
But eventually, yeah, we get transactions from the pool. And yep. Interesting things. Okay, so yeah, we have this method which is process transaction. We can go to it. And well, we basically prepare kind of a lot of context. But the important stuff, just this one. We end up here, which, I mean, again, preparing metadata. So, but basically here, we create this struct that has, in order to process a batch, we need some metadata, kind of the block header stuff, but with some special things related to the zk things. And later on, and here's where we jump to the executor. Now the executor, maybe Frances can follow, but essentially the actual EVM and Merkle tree implementation are done in a separated repo, which is something quite special from our project. As in, we don't have the EVM directly on the node, but we share the same EVM and Merkle tree for the zk stuff. So at this point, we are not dealing with zk. We are just trying to understand the outcome of processing a transaction. But we engineer the whole thing. Yeah, okay, Victoria, go ahead.
Yeah. Let me explain that because this is important. So we don't have two versions of the processor, so of the consensus. What we understand of consensus. So consensus is you get the transactions and you compute a new state. Okay. Here, we are having a single. We call this executor. Okay, because it's just taking transactions and it's executing these transactions and computing a new state. The executor of the node and the executor of the prover is exactly the same, and it's the same code. We don't have two versions of a consensus in this version. So all the consensus is done in the same code. That actually is a code that executes this ROM. Okay, so it's just taking the transactions and it's executing this ROM, and the result. So the result of the prover and the result of the node is exactly the same. So we are dealing with this, and this is why there is this calls in here. Okay.
Sure.
So this is a design. This, and maybe in the future we can do maybe a more optimized version of this executor. But in this version, we wanted to be sure that there is no conflict, no consensus conflicts. So I cannot promise to a user that this is the current state, and then the prover says another thing. Okay, and the prover puts another state that he thinks. Yeah. So in order to be sure with that, we are using exactly the same code. In one side and another is the code that's rated in C, and then the node is just with an RPC call is just calling this, and we call this process an executor because actually it's usually taking transactions and it executes these transactions and computes this new state. But it's not computing the proof in the normal. When you are building the block, you're not computing the proof. You are just building this. You are computing this new. You are just computing this new state.
And so this is actually running your processor under the hood, or is this?
Yeah, it's running our processor under the hood. It's doing it. The only thing is not generating the proof itself.
Sure.
So
that makes sense.
But it does exactly. But the code is exactly the same code that the prover will use to compute the proof. So there is no there is no possibility that there is a mismatch between what the prover is proving and what the user is seeing in there.
Okay, that makes sense.
So essentially, we don't have the EVM implemented in Go, but in zk assembly.
Right.
So yeah, Frances, maybe you can follow up and keep up the flow from the now we pass the ball to the executor.
I like this tag team process here.
Okay, let me see. Mm. Okay, I'm going to use the GitHub repo because the objective was to get familiar with the repositories. So I'm going to jump to the zkEVM prover repo. This is where the C++ version of the prover lives. We have also the prover.js repo, which is the JavaScript version, and most of the source code is under the source directory, and this gRPC is the service the services directory. We have three main directories, services. You can forget about this one. So far, this is something new we are working on. But essentially, the prover is a binary that exports up to 3 different gRPC services, which are these 3 ones. One is the stateDB. The stateDB is to access the database. You can store data there. For instance, during the Genesis, you can also access the DSMT, the sparse Merkle tree that we use to store the state. You can read and write to the tree. And this is done through the prover. Okay. The executor is the service that we have just seen that Arnaud's code was calling. We will look at this in a minute. And then we have the prover service, which is the one to generate the proof. Okay, it's the same binary with 3 possible services. Which one do we offer? It depends on a configuration file that you can find in the test vectors folder. And this configuration file tells you if you want to be a stateDB service, an executor service, or a prover, or a combination of them. Normally, these 2, they don't require a lot of a powerful server, but they need to be sequential. So we create an instance of them in an average server. But this one, the prover, is the one that generates the proof. So there's a lot of calculus involved. And then we use a powerful server. Actually, we create several instances of the prover to calculate all the proofs. Okay. If the executor takes a few seconds to generate, to process a batch, the prover maybe takes a few minutes. So that's the big difference.
Got
And
it.
here,
Would you mind zooming in just a little bit?
Sorry.
No, that's perfect. All right.
Okay. And here, well, this is a protobuf syntaxes, but essentially this is a request to process a batch. Okay, here the sequencer says, okay, these are a few transactions that I want to process to see if they fit into the maximum number of evaluations that we can run into our state machines or into the cache that we have available. I mean, with all the constraints we have, we can process this. Okay, and this is the input data, like the all state root. With this, we can navigate into the system. Okay, and we generate a response, and the response. Well, this is the data. Actually, this is the batch layer 2 data. Here is where all the transactions are. This is like a buffer of transactions, and we return the new state. And we return a number. Well, of course, we return the results if everything went well, or if we run out of gas, for instance, or if we run out of the maximum number of binary operations that we can process, whatever. Okay, and these counters are important. So the sequencer calls this method a few times until it right sizes the amount of transactions that we can put into a single batch. Okay, this is something sequential and very, very fast. It's a ping pong protocol. And after that, we say that we have a batch that we can process. Okay, this is very different to, for example, the prover proto, in which you can generate a proof, and we have an input. I mean, the same data that we provided before. It's provided here in the Jane proof request, but the Jane proof request returns immediately, and after that you need to pull the service to get the request. And the request, and the response to this request is a proof actually. Okay, it's a proof, and it contains all the data required to verify that the operations were properly calculated.
Okay.
Okay.
Great. And so, yeah, can we dive into the executor and how it?
Yeah. Here, so the idea is that we already have a batch that's somehow created. Okay. So the next step is to send this batch to the blockchain. Okay. So maybe we can go to the smart contracts and see how these. So the executor just send this batch to the blockchain. Let me share the screen, and then this goes to the.
I think that it would be. I think it would be interesting to see how the executor works under the hood. Like we have been seeing the interface, but not what's behind it. I don't know.
Yeah. I'm interested in just
as you want
briefly.
As you want. Yeah, maybe you can go briefly there, and then we can jump to the smart contracts.
Okay, let's go back to the code. Let's jump here. Okay. This is the source directory, and we have the executor. Okay, the executor is the one that calls all the state machines. When we generate a proof, we need to call all the state machines. We have 14 state machines in total. Okay, some of them are bigger, some of them are smaller. We have the main state machine, which is the one that says, okay, this is the result of the operation. But then every time we call an operation that cannot be verified using the polynomials, the evidences generated by the main state machine, we need to delegate this work of verification to a customized, a specific state machine that is designed specifically for that work. For instance, the arithmetic calculations or the storage. The storage is a very specialized. They are like co-processors of the main processor.
This is what we were talking about earlier with special purpose circuits for particularly hairy math.
Correct.
Okay.
So the process batch, this is at the end what the service calls we just saw. At the end they call this is the executor process batch, and this one calls the main executor, the main state machine executor, with the polynomials and with some data that is okay. I cannot prove this, so I need some other state machine to generate evidences for this operation. So this is stored here. Okay, and this is the input request. We will take a very fast look at this, but it is important to know that in this case we are only calling the main state machine executor. Okay, the big one.
Okay.
Not the other 15, and we are not generating the proof. We are just like doing a pre-parsing, saying, okay, I can process all this. It works. I know that I will be able to digest this when I generate the proof afterwards. So this is okay, or it is not okay. It depends.
Okay.
But we are only calling this one. While if wait. Okay, let's stop here. But when we call execute, when we are generating a proof, we actually call the main state machine executor, but we also need to call the rest of the state machines.
Right.
Okay. With the output data of one state machine, we call as an input another state machine. And that is a dependency. There's actually a tree of dependencies, and this can be called in a serial way, or we just can generate threads and we process in parallel. It's actually the default behavior right now. We process in parallel all the state machines, and then we get the aggregated committed polynomials of all of them and we pass this to the part of the prover that generates the proof. Okay.
Got it. Okay.
And very quickly, under the SM state machine folder, you can find all these state machines. This is the main one. And here, the most interesting file is the main executor, the one that we just saw being called from the executor. And here, what we do, okay. What we do is for every, for all the evaluations, what we do is to take the ROM line, and this is the line of the ROM that we have loaded into memory. The
This
ROM
is a
comes in a
ROM,
ROM.
the compiled EVM ROM,
Right.
written for your ZK.
This is in JSON in JSON format, so it's very human readable. You can actually read the ROM,
Sure.
and you can identify the zkEVM code, how it is compiled, and it generates the JSON data. So we load this JSON data into memory, and here we do things with that data. For instance, let's see, we want to, this is a selector. We want to do this. We want to set the register A into the OP register. OP is like the accumulator, internal accumulator. Okay, if this line of code tell us to do so, we just copy the data. Actually, every register is actually 8 registers because we use the Goldilocks field elements, and we just take advantage of the lower 32 bits. So we need 8 to cover the 256 bits in total. Same thing if we do a B. Then let's say we want to calculate A divided by B. So we call the instruction, and then we store the result in C, let's say. All this is done in this code. This is very mechanical, except the division part, because the division part is something that we cannot prove here. So we later on call the arithmetic state machines to prove that the division is correct. Okay.
Interesting. So this is actually your, here you're actually taking the instructions and you're translating that into
polynomials.
Yeah, we are processing a ROM, and we are creating a trace, which is the polynomials.
Got it.
Okay.
For example,
so and this is the processor, is the
right.
what it process.
For example, in this evaluation, the evaluation I, we log that we had in the polynomial is set to 1 or to whatever value we have here. Actually, we can multiply this by the value. This means that the rest of polynomials must match this functionality. So you cannot put any value you want in the OP and then store this into D. So, I mean, the value of B and D will have to be the same because you are setting this to 1, and then you are copying this into OP, and then you are copying the OP into D, and set D is set to 1. So everything needs to match. There's no possible mistake here. Otherwise, the validation will not work. So we generate millions of values of committed polynomials with all the detailed values during the computation, so that later on we can just show the trace. Yeah. Everything is clear.
So, and these polynomials, so at the end, all this trace is a set of polynomials, and then with the pill, what actually is saying the relationship that these polynomials must fulfill, which is actually the processor itself. So this is what's validated in the zero knowledge. Okay, but this is very, the result here is just an array of values. So here is not, at the end, until here is a program that's executing, but the trace is just an array of a lot of values. Okay, and the executor what's doing is executing this ROM, and this, maybe Frances you can show that, but this program is exactly the same that's used in. So we can call it this program from the prover, which it generates all these trays and everything. But we can call this program in a simple way, so that you don't keep all these trays. You don't do most of. So you just execute the program, and that's it, because you are interested only in the result. Okay, and this is where the executor is coming. And this is important because in this fast way, you don't compute you don't care about the auxiliary the coprocessors, the auxiliary state machines and so on. So it's just executing. It's a version of this code it's this code that with some ifs that they just don't do anything else. That just but it's executed exactly the same way. So it's taking the ROM and it's executed.
Yes.
Right.
Yes.
So you're not. Are you actually doing anything with these polynomials if you're running it outside of the context of the proof, or do you just throw that away?
We are not even storing them.
I see. Okay. So you get the result out. You get the result out. You throw out all the rest of the outputs. Okay.
Okay. But that's the same code. The important part is that's the same. So we are executing the same code, which is the consensus is what.
Right. That makes yes. Okay. And by the way, I don't know how much time you have. I can go for a little bit longer, but I don't want to keep you for too long.
Let me show you maybe the smart contracts, which I think is something.
All right, let's take a look at the smart contracts.
Yeah. So here I'm connecting to the public testnet. Okay. So this is a smart contract on the public testnet. So actually, you can see the code here because it's verified here. So you have the code here. Okay. And here in this smart contract, you see this in Go early. Okay. We are working the public testnet is in Go early, and here you see mainly two transactions that we already saw before. The sequence batches. If you see the sequence batch, this is where the sequencer just get the batches and just publish that availability on there. So if you see here are all the you can see here all the transactions. So they are encoded, but here are all the transactions that are sequenced.
Just to ask quickly, so, are you posting the raw input data, or are you posting state diffs?
This is just here Carlos may explain, but this is just the transactions. So it's the raw transaction, including even the signature here.
Okay.
So it's just an array of transactions. Mainly here we are posting something else. We have, for example, for the bridge, we are putting also what we call the global root of all the deposits that are making there. We are putting here also the timestamp because the sequencer may commit to some timestamp. So here we are also putting the timestamp. There are some details, but this is these things is the timestamp, the global root, and all the transactions of a batch. We have and here is an array of batches, so you can post many batches at a time here. Okay.
Sure.
But this transaction is doing not much. It's just it's data availability. They are just putting the data there. It's not computing anything. They are just putting there. This data even could be wrong. It just could be some random data. Okay, but this random data in a consensus way. So the prover will prove that if it's an invalid transaction, for example, that's okay. So that's okay. This is going to be an operation transaction, but they will move forward. They compute the new state. So it's whatever data you put here, you should be able to compute a new proof. Okay. So the only limit. So here the only thing that a proof cannot do, but is done in the smart contract, is the limit the total batch. So the size of all the data. Okay. So if the data is billions, maybe we cannot fit that in the proof. But as far as the data is limited to size, I think it's something like 32K or something like that currently, we guarantee that you will be able to prove a new state out of this data.
So no matter what the data is, if it's valid, invalid,
no matter what the data is, if it's invalid, if it's an invalid node, it's going to be a no operation. Okay.
Sure.
So the sequencer has the incentive not to put these transactions because they will not get any fee from these transactions, from these invalid transactions. But the system will move forward. The state is
sure.
You're
not going to get locked up. You're not going to be able to not prove the thing.
Exactly.
Okay.
And actually, this is important because, for example, in the system, anybody can put a transaction in layer 1. So I can force. This is what we call force transactions. I can put a transaction, whatever it is, in the layer 1, and then the sequencer has the obligation by smart contract to include this transaction. If they don't put this transaction, they will not be able to send more transactions. So this is a way to guarantee that
you actually block sequencers from submitting to this smart contract.
No. It's
or
like,
is it?
No. It's like it's the sequencer. You either process these forced transactions, or you cannot do anything. So you can stop. So you cannot stop a user for making a withdrawal, or making a transfer. So a forced transaction, of course, the user will have to pay the layer 1 fees. Okay? But once the transaction sends a forced transaction on layer 1, the sequencer will be forced. So this transaction, you have the guarantee that this transaction at some point is going to be included in the post. And if it's not included, it's going to be a timeout, and you will be able to include it. So in the worst case scenario, even if the sequencer just stops running, you will be able to be a sequencer and
so you can prove it yourself.
Here we have a warranty.
I see.
Yeah, you can. Here is what we are guaranteeing, that the money, that the value is not going to be locked in there. So I cannot. Here is the. So it's a censorship resistance. Here we can distinguish between two censorship resistance. So it's censorship resistance in the sense that I cannot lock you. I cannot block you. What I can do is prevent that you are using the system in a regular way. Okay, so this it's not universal. So it's like if I don't want you to let you use the system, maybe you will be able to withdraw, or you can use the system. You will have to pay a layer 1 fee every time. So it's like this thing. So I can force. So it's not really like a true censorship resistance. It's not perfect, but it's a censorship resistance in this sense. Okay. Other thing is we add a decentralized sequencer, which is it's another story. But even for the centralized sequencer, the system is censorship resistance at this level. Okay. So here is the transactions, which is not much. Okay. Just for that availability, and then the others here are the batch, the provers. Okay, so here you can see actually where the proof at the end is. You cannot see well. At the end is a proof. At this point, it's a gross 16. So this is just a single proof. But actually this proof validates that this new state is valid, and actually put this state on chain.
That's pretty cheap.
Okay, so
300,000 gas is cheap.
Yeah, 8,000. Yeah. Yeah, it's a gross 16 validation. That's it. And actually we are here. It's not in the testnet yet, but we'll put. We can aggregate many. Right now it's a proof per batch. Okay, but we are going to put probably in a few weeks. We're going to put a proof that aggregates many batches, so that you can have a proof with 1,000 batches or something like that. So it's like I would expect that maybe it's a proof every 2 hours, so every 3 hours, and this will include all the batches during these 3 hours.
Sure.
Okay. This is very much. So this is the smart contract. Of course, here is the bridge, but yeah, I don't know. Here is as you see, there is a lot of code, and there is a lot of pieces there. The team is it's quite big and so on. I don't know if you're interested in going to some of the pieces or whatever. Here is we can go, but yeah, do you see at least the big pieces?
Yeah, I understand the big.
You may have an idea.
Yeah. No, I think the big pieces make sense now. So that's. I think we got some.
Of course, you go each piece. You can go to each state machine. It's
sure.
It has its own story. You can go to the storage, for example, the storage state machine. It's a processor itself that's processing this sparse circuitry. All the arithmetization, it's a full story on there. if you go to the ROM, of course, each opcode is a full story. As a mul mod, or each how you compute the kechecks and the hashes. It's a full story. How you store the programs, it's a full story. How you deal with, there is a lot of this. How you deal with timestamps. How you deal the bridge. The bridge is like a full story. So you see that there is many pieces. Okay?
Yeah,
and each
there's
one
a lot.
It's actually, you need to think that this has been it's about 30 developers 1 year. Okay, so this 30 years of development is what's in here, more or less.
Right. No, it makes sense. It's interesting. Obviously, there's a lot of parallels with what Optimism is doing, but there's some interesting differences. Well, maybe, sort of. I think the biggest, obviously, you're constrained by your proof, right? This is
that's okay. It's what.
Yeah, right.
But I would say that optimistic rollups, they are also, the constraint is the fraud proof. So it's you need to generate a fast, and a fast and easy fraud proof. So probably different constraints, but at the end you need to do something to deal with that.
Yeah, you're constrained to an extent. I think there's a I think you're less constrained, and that opens up this door to maybe a shift of thinking about well, how do you describe this? I think a significant difference, or a subtle difference that I think is it reveals something interesting is inclusion of these force inclusion transactions, right? So in Optimism, in the upcoming Bedrock design, you don't need two steps in the force inclusion process, and traditionally you did, where you have the first step where you say, here's a transaction. If you don't include it within, an hour or whatever, then I'm allowed to I'm allowed to send a second transaction and include it in the chain. In Bedrock, it's more like, here's a transaction. If you don't include it within an hour, then the definition of the chain is that if you include anything but this thing, then the chain is not, what you're posting is garbage. And to do that, you need to be aware of the state of layer 1 in how you sort of derive what your layer 2 looks like, which is. But but that's something you can only really do because you aren't constrained. You can basically do your proof over a significant amount of parsing and execution of the layer 1 chain, which is, well, it introduces other issues, but it's sort of I don't know how much it matters at the end, but it's a subtle point that.
Well, here this execution is in the cases of first zkEVM rollup. If you want to have the warranty before the proof is generated, you have to run. But the thing is that maybe the time is going to be shorter because maybe you need to synchronize maybe 1 hour, 2 hours, so since the last proof.
Mm-hmm.
And this is probably this timing is going to be slightly lower, 2 weeks,
right.
3 weeks to roll up. That's probably a difference. But yeah, well, you see, this is what we are learning,
Yeah. No. There are these subtle differences, but it's funny. I think at a high level so far, I probably have to close this out soon. At least today's session, unless people want to come back another day and do a deep dive into more code.
If you are interested, we are absolutely open. As you know, we are
sure.
now we are working in the audit mainly at this point. So the idea is to explain the code and explain the code to anybody as much as we can. This is the main priority. Well, we want to first to freeze the code yet, because there are some pieces that we want to clean up and freeze there. But let's say that in a month or so, we should be 100% focus all the team to explain the code to auditors, people that checking, that reviewing. So here, anything that you see that could be interesting, we're absolutely open.
All right. Well, then the chat says in all caps, "We want more." So that's a good thing. Cool. Okay. Let's. Yeah, I'd love to do this again and to dive again into. I don't know. There's so many different components here that we could possibly dive into. I'm sure you could spend months looking at this.
Yeah, we can focus. Maybe if there are some interest on some specific components, maybe we can go to a deep detail of some of the components. I don't know, some state machine in concrete, or some smart contract, or some maybe in the node. Just whatever it's interest, and just we can organize another. That's great.
Cool. I'll poll people.
Perfect.
All right, fantastic. Yeah, I think this is a good, maybe a little deeper than high level overview. So I feel like I get the components. I get what it's made of now. So that's nice. It's this has been great. I think somebody is going to get mad at me because I have a meeting as of 2 minutes ago, but. That's okay. That's just how this goes. But yeah, we should do this again, and maybe dive into something. We'll see what Twitter wants. Thank you again. This has been great. Shout out to the Polygon team, of course. This is very cool. This is definitely, like if I were going to build a zkEVM today, probably close to how I would build it. So this is, it's a pleasant surprise to see the architecture.
Perfect. A pleasure to be here, man.
Yes.
Thank you.
Thank you, Kelvin, and everyone.
Yeah. Thanks, everybody. The chat says thank you to all of you as well. So this has been great. All right. I'm going to go upload this or whatever. So have a wonderful Thursday or whatever day it is. Well, yeah, it is Thursday. And see you on Twitter, probably.
Perfect.
Cool.
Okay.
Right. See you.
Bye,
See you. Bye, Kelvin. Bye.
Bye.
Alrighty. Which window capture am I? All right, everybody. That was wait. Oh, I hid myself. Give me. That was session number 1. Seems like it's going to be session number 1 of probably a few sessions. I think it was pretty good. I think we got a good overview of how the architecture works. A lot of information in there, but it makes sense. We can do a recap next time, but at a high level, they have a processor, a zk processor, sort of like their own sort of fantasy virtual machine that they've built, and they build the EVM in assembly on top of that processor, and then they run it. It strikes me as very, very similar to what Arbitrum used to do with the AVM. So that intuitively tells me it's probably going to change. I mean, of course it is. I think the ZK systems are probably going to look a lot more like the optimistic systems are eventually once we're able to get a little more efficient with the proof systems. But yeah, it's funny to see history kind of repeating itself. At least the nice thing about history repeating itself is that you have a clear idea of what the future is going to look like, because other people have already gone down those paths. So Cool stuff. Great session number 1. Thank you for showing up, and we will probably, it sounds like, do a session number 2 with the Polygon team to dive into more code next time. So thank you. Have a wonderful rest of your Thursday, and see you next time.